Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so very happy to have Bernard Chazelle from Princeton. Bernard has worked extensively on very unnatural algorithms in the past. And today he's going to tell us what natural algorithms are.
Well, thank you. From this, I can only...
And you'll return the paper sometime.
Yeah, I will, certainly. All right. I've never been here before. This is a brand new building for me and so on, but I recognize quite a few of the faces. So it's like same actors, but different play in different setting. So this is what I will talk about, make a natural algorithms more natural. So it's often asked, what's the difference between science and engineering? I think that's easy to answer. Science is the study of nature as its own end, for its own sake, and engineering is study of nature with the goal in mind, as a means to an end, and you want to do something with it. So you can ask, well, is math science or engineering? And I think it's clear it's really both, because you've got the prime numbers would be like the stars. You don't get to choose them, really. Unfortunately, they are what they are. But these you get to choose. I mean, first of all, it is a piece of mathematics. There's no doubt about it. On the other hand, it's used like a bridge, not like a star. In other words, it's used simply to accomplish a task. And
Bernard, can you check the mic? Is it on?
where's my... Yeah, I mean...
They can turn it up. I mean, the main reason for it is so that we can broadcast it. And
Yeah, so
record it.
the mic is not for us, is it?
It is.
Well, he can turn it up if
Wait.
we do
Oh,
need a
no.
mic
Maybe we
for
can
us.
turn it up a bit.
Jeff?
All right, sounds good. Okay, it'll be done.
He's hiding
Yes,
right
it
here.
is.
Okay, all right. Oh, yeah, I can hear myself. Okay, all right. So, what? It's too loud. Very picky audience here. Oh my God, the decibel level is really upsetting me. Okay, so an algorithm is designed by humans as a means to an end, and so one would think that an algorithm, therefore, as a piece of mathematics, is also a part of engineering. But I want to question this assumption. That's the purpose of this talk. And let me show you some algorithms. This is a circuit, but it's an algorithm. This is what prevents you from getting cancer, and it's a protein. This is your brain. You can think of it as a giant sort of algorithm. So it's pretty scary. It's just after Halloween. This has two algorithms. There's this neat algorithm that produces this foliage. But then there's these two guys, the two ants. You know, ants and bacteria are the two most evolved creatures on Earth. So these are pretty neat algorithms. This is a less neat algorithm. It's not Boston, but it could be Boston. This is a lovely school of fish, transparent school of fish. Well, I think you get the point. So these are natural algorithms. We don't get to choose them, really. So they're like the stars, and they should be studied as such, okay, just like we study the prime numbers. And this is therefore very different from studying bubble sort, my favorite unnatural algorithm. Not yet, but we're getting there. Actually, we fought a battle to get out of engineering, which we lost, but part two. So if you look at Google PageRank, you know, it was designed with fewer than 100 designers over 10 years. And as I said this, I just realized that this is not Google. This is Microsoft. This is terrible. So let me fix this.
Well, maybe Bing is natural.
Yes. Okay. Good. So Bing. Well, thank you so much. And I promise we did not rehearse this. Now, Bing took fewer than 100,000 designers, a bit less than 100 years. Now you have to compare this with that, which took over 1,000 trillion designers. There's probably a word for that, 1,000 trillion, and over 100 million years. So it's a different, yeah. Oh, I also have a line about this. You two are dangerous. You must have seen my slides in some kind of ESP thing before. So So the reason why they're so cool, not that Bing is not cool, but I mean a certain level of coolness, if Bing is here, the others are somewhere near Pluto. They're very, very cool. And is that natural selection is the ultimate software optimizer. And now I'm assuming you all believe in evolution theory, but nowadays you can't just assume that, especially with the Republicans in charge of the House. So for those who don't, whatever makes you believe in yourself and in life, that is the ultimate software optimizer. I guarantee you that. So there are two issues here. Well, at least two issues here. The first, if this is a natural algorithm, where is the code? That's a good question, which I will punt. Let's just postpone that for another day. The second is, what are the tools we have to study those animals, to actually study, not just the animals, the birds, but to study natural algorithms? And so that's a sore topic, which I will address now. But we have three kinds of ways. You can go back to Boltzmann's, 19th century, and you have statistical mechanics. I don't have to tell these people in front row about that, but this is really offers extremely powerful tools to study a whole class of natural algorithms. Now there's also another way of looking at it, which is different. It overlaps, but it's different. Is that of dynamics, that of dynamical systems, and gives a very powerful mathematical set of tools. Now there's another one which is simply computational thinking. I'll get to this. Don't ask a question if you think I might answer it without your asking it. So just remember. Now you may have you may have noticed that this is smaller than this. This is not just because I have not mastered PowerPoint amplification thing. It's because this is Alan Turing, and because it is my sense that this contribution to this project has so far been greatly underplayed. Hence, my presence here today. Now, see, so that I could do. Although I don't know how to improve the pixelation there, but anyway. Well, thank you. They're all dead. I mean, if they're all alive, I might actually worry about getting them straight. Yeah. This is going to be a tough one. Okay. Now, you might want to ask, but don't do it loud. Why is an algorithmic approach needed? Okay. Now that I will postpone until the end of the talk, if there is an end to this talk. And but first, let me give you some results. This is something you can chew on, or think about, or sleep on. Bird flocking, firefly synchronization, and opinion dynamics. So I'm just going to give you some results. First one. Yes. So, and this is a video of starlings. This happens near Oxford in England. And what happens is around 7 p.m. every day during a certain season, about 1 million starlings get together before they go to bed, before they roost. They do this thing. Now, scientists don't know why, but they won't tell you they don't know why. So they speculate on all kinds of things why they might be doing this. And no of these speculation I have found very convincing, but who knows? Basically, I don't think we really know why they do what they're doing. My hunch is they're auditioning for the Bolshoi ballet or something like that. And so they do this for a while. And what's remarkable is that if you've ever taught discrete mathematics, you probably taught the birthday paradox that says this cannot happen because they've never observed a collision ever. There's 1 million. Just think 1 million choose 2. There's a lot of possibility for collisions. They've never seen a bird falling off because of a collision. And yeah, they go through each other. This is unbelievable. Yes, and they never collide. Just imagine if this was your plane flying out of Boston. So this is just remarkable. if you're a physicist, you might want to see a gas that kind of follows some kind of Navier-Stokes-like thing. Where if you're dynamics, well, see, everybody's going to see something different. And so some people have looked at this, some mathematicians and physicists, and proposed models to study this. Of course, there's oversimplified model, as we have to, because we want to get our toe wet and see what happens. These are obviously very complex phenomena. So the typical way they go about it is they say, well, let's get a graph out of this. And so every bird will interact with some of its neighbors. So maybe to make things very simple, we'll just draw, there's the magic radius, and every bird is influenced by its neighbors within a certain distance. So you draw this communication network, which at any given time will tell you which pairs of birds interact. And this graph will change over time, hence the word temporal, in some sort of feedback loop, because of course it'll change according to what the birds do. And so you want to study this graph. So now the actual motion, and there are several variations on the model. It could be, for example, the velocity of this guy will average itself out in the next step with its friends. So because it's just trying to orient itself with its friends. And maybe there's also some potential function that keeps birds from being too far apart, but also keeps them from being too close, because they don't want to collide, especially when you fly. Collision is not a good thing. So see, I hope you didn't miss this. If you blinked, you missed it. So let me do it again. See, this move. And so that's how they fly. And so you want to ask questions. For example, if you look at this network, you can ask, well, does it remain connected? Or if not, let's call a flock a connected component. And how many flocks do you have at the end? Does it ever settle? Maybe it does not settle. Maybe it's just, okay, these kind of questions. So now here's what I showed is that this thing will start in a very mysterious way. Almost anything can happen. Flocks will aggregate and disaggregate and fragment and all of that. But after a while, what will happen is they will form flocks, and flocks will only be able to merge. They will no longer be able to split apart. And after that happens, they reach steady state. So there's just, everybody is in a flock. The network within each flock will no longer change ever. And they just go on like this forever within this model. Okay, I'm not saying this is the way birds do things. And so the timeline goes like this. There's a period of fragmentation. There's a merge phase. And then you reach steady state. And when you ask how long it takes to reach that steady state, you get this very strange function, which is a tower of 2, height being the log of the number of birds, which is not the first function that comes to mind when you think of birds, and maybe the second. But what's very strange that this is actually optimal. This bound is tight. And so, of course, it doesn't say anything about birds.
What way?
So I'll tell you in what way. That with this model, it's possible, if you give me n birds, I can give them initial position and velocity so that you will have to wait this long to see the last merge into one last flock. It will not happen before.
When you have two flocks going in opposite directions, so let's say your starting condition is one flock at minus infinity, well, almost minus
Yes.
infinity, other at plus infinity,
Yes.
going in opposite
Yes.
direction. Do they fly in your model through each other, or do they, when they meet in the middle, half of them turn around and they're one flock?
They will fly through each other, yes. But we assume that this is in more than one dimension. We assume that the birds are particles, they're points. So we assume 2 points don't actually bump into each other. That would be unlikely if they're actual points. But yes, on one line they will go through each other. I'm sorry?
For while they go through each other, suddenly they look like one flock.
Yeah, exactly. But then if they go too fast, they might break apart. If they go slowly, they might. You have to think of this as springs with glue. Because just as you said, when two flocks go, if they go very fast, by the time they realize the glue should keep them together, the inertia is too big. But if they go slowly, they will realize, and then they will start moving together. Yeah, so you can have this strange phenomenon. Now, from a computer scientist, the way you want to look at this is the following. We look at computers, we look at birds flying as computers. There are certain kind of computers, and computers compute. And there's something called the busy beaver function, which we all love as computer scientists, which is given some form of models of computer. What is the longest time, given a certain input of certain size, what is the longest time this machine can run without falling, without either stopping or falling into an infinite loop? Because it's easy to run for infinity. But it's not easy to run for a long time without getting into an infinite loop or stopping. So this is the busy this is the optimal busy beaver function of that computer, if you will, or that bird-like computer. In that sense, it is optimal. It's not optimal in the sense that if you look at birds on the charts, they will actually have this sort of behavior. So it just, if anything, it shows the enormous gap between the models, the mathematical models we have, and reality. So there's a huge, huge gap, and there's no question. But I don't really want to talk about bird flocking, so I'll just move on. I just say lots of previous work, really, really lots of it, and I don't have space to mention this. But the difference is that everything else before makes assumptions on connectivity, which, in my view, is completely missing the whole point, because they will assume that, say, every pair of birds will communicate infinitely often. We just assume that. But that's the whole point, to know whether this will happen. So once you assume that, you kind of given the game away. What's really interesting is to find out whether this happens or not. That's the key question. Number 2 is firefly synchronization. Now, this does not look like fireflies much. These are metronomes on coke. And, well, sorry, I didn't mean this as a joke, but actually it's not a bad one. And so what happened is these metronomes beat at the same frequency, but not in the same phase. I mean, they started like random phase, but if you wait long enough, you will see that eventually they all get to beat exactly at the same phase. And now the coke is very important because Dr. Pepper would not work. No, this is a joke. If you hold it with your hand, this will not work, okay? Because you see, these metronomes are talking to each other. That's the way you should think about it. And to talk, they need the wood, but the wood will not resonate the right way if it's not on something very solid like a can of coke. So if you actually hold it, you will kind of dissipate all that energy, and so it won't work. So now what you have here are 3 coupled oscillators, and they talk to each other through a very simple network, which never changes. It's static, is just this. This is the network. Now, this Hungarian composer, who died not long ago, actually, and was quite famous, and composed this lovely concerto. You can listen to it on YouTube, which is a concerto for, modern music is a little different from ancient music. So it's a concerto for metronomes. I mean, usually metronome is not used to produce the music, but it is. So you have all these metronomes, and he plays off that effect of synchronization. And it's quite striking, actually. And
can we hear it? Or are you gonna
yeah, but not here, because I don't have an audio system. But if you go to YouTube, type his name and you'll see. No. Well, maybe.
That would be great.
How are they synchronized in this ligative piece?
What?
How are they coupled?
What are they sitting on?
Oh, they're sitting on wood. That's
But
it.
Again, it's
on-
the vibration.
But not on.
But it's set up in some way
Yeah.
so
To be
that
the
it
truth,
doesn't
I've
dance
never
the
seen it
coupling.
in real life. I've just seen the video, so I think they're sitting on. But something that I want to mention there's a huge difference between the West and the East, Eastern Europe, Western Europe. No, this is not funny at all. This is serious. Or you don't laugh before the joke. But which is, no, this is science. We'll just do science here. Which is, well, Eva can tell me maybe they've changed. But in the olden times, in Eastern Europe, at the symphony orchestra, when you applaud in synchrony. Whereas in the West, it's completely chaotic. I mean, you just clap your hands as you feel like it, and it's just like this cacophonic, whatever. But in the East, I guess they teach their kids differently, and they say, just try to do it like the guy who's sitting next to you and the woman who's sitting next to you. Right? And if you just do that simple change in your mind, very quickly in 30 seconds, everybody will be clapping at the same time. And so, anyway. So here the communication network would be fixed once and for all, but it would be more complex than just three nodes. Now this guy, Sir Francis Drake, went about the world in a boat and discovered all sorts of things. He was also a pirate and all sorts of interesting things. But he discovered this phenomenon in Thailand, which is really remarkable, that there would be fireflies that start flashing in synchrony along the riverbed. But this would go for miles. He could see it from a hill, and he could see this thing just go on in synchrony over miles. And he was so surprised. He wrote he wrote about it. He wrote his, his journal, and then he tried to convince his friends in England that what he'd seen, and nobody believed him at all. They thought, oh well, you must have been drinking too much rum because they do a lot of drinking on these boats. He said, no, I swear, I did not do too much drinking at the time. I saw it, and this is what happened. So this poor guy, nobody could believe him. This is a bit like if he'd proven P is not NP and somehow nobody would believe it or something. And so, but except that this was true. And so it was really, people rediscovered that. Now this film is not about the Thailand thing. This is just a tree. And now the phenomenon in Thailand happens in other countries, but very few, Malaysia and a few others, but basically not in the West. And this is just, firefly that flash in synchrony. So they flash, you've seen this. But if you wait for a while,
Between the East and the West.
that's another difference. There you go. See, this is all.
Western fireflies.
No, yeah, I mean, it's obviously.
So this is a picture taken in the east.
Yes. Of,
So have they tried moving those fireflies? No,
yeah,
I'm
well,
actually-
they stole some, and the guy tried it in his hotel room. But I mean, not Drake, more recent scientist, and it worked, but not at the scale. I mean, what's remarkable is that they can do this over miles, literally
is it
miles.
genetic, do they think that those fireflies are genetically capable of doing
Yes, there must be.
or not?
Yeah, there must be. But to be honest, I don't really know. And though the good thing is nobody knows anything anyway, so I might as well just speculate. But
Good for science.
but at least they believe him because now in fact, the New York Times last week had an article saying that because of global warming, it's harder and harder to find these fireflies, and it gets smaller and smaller. So if you didn't think global warming was a serious issue, now I beg you to reconsider.
So wouldn't it be much more natural theory to say in these areas that didn't have sort of yet as much electricity and the night was darker and nobody, if you're in New York
What?
City and you're flashing, you sort of disturbed by all the other lights.
I mean, when
No,
you're
that's
in New
true.
York City flashing,
That's true.
You disturb everyone.
I mean, I don't know if it's true, but that makes sense. I mean, I don't see why not. You'd be, yeah, because they're very sensitive to the light. So yeah, if they're like taxi drivers, just keep on flashing their, yeah. So, anyway, so 3 is opinion dynamics. I've got to check this time because I'm a little bit worried here. So it's a different problem, I guess,
You
which
know
is,
that you go till 5:30 now. Well, I mean, with questions, with
Oh, my God.
interruptions.
now I'm going to have to speak very slowly now.
No, but I mean, we can interrupt you.
Oh, all
more
right,
than
okay.
enough
So I
time.
shouldn't worry that somehow I've got 5 minutes left, and I still
Not
have
at all, no.
I still have
but I mean,
135
but
slides.
We do this so that when we mess up somebody's talk, we actually give them time to finish.
Well, thank you. It's very generous.
What? We give ourselves time.
So there's this model that was devised by these scholars, one of whom is a philosopher, Hexelman and Krause, and to to make predictions about, to understand why people change their minds and why they agree on anything. So let's say that you try to find yourself on the political spectrum. So you could be, so let's say there's a scale from 0 to 1. If you're 0, you're kind of on the left. And if you're 1, well, you're kind of on the right. And now you try, I don't know where you are. So now, if you're just on your own, it's not clear why you should change your mind. But what happens is you're going to be with a lot of people all along this thing. Now, the assumption these people make, which is questionable, but it's not, it's reasonable assumption, which is that you're only influenced by people who are kind of like-minded. In other words, if we disagree but mildly, you're likely to listen to my arguments and maybe adjust yours. But if you think I'm somewhere in cuckoo land out there, telling you about the flying spaghetti monster, you're unlikely to change your faith system to meet me halfway with the flying spaghetti monster. I mean, you just say, okay, good for you, So maybe it makes sense. So you see what happens is everybody here has some influence radius. So let's say this one here will listen to the people that are 0.1 to on the right
Do they
wing of the
listen
spectrum.
With a uniform
So
listening or not, or does it
yes.
fall? Yeah.
So let's assume right now, for the time being, that everybody is equally influenceable. So the same radius applies. Let's assume that. That's an assumption
So
right now.
everyone within that radius is equally influenceable. Or like,
that-
does that
okay.
guy's influence fall off with the distance from him or not?
So that we could allow, yes, that we could allow. That I have no problem. I have no problem if you have this falling off with a thing. But right now, what I have a problem is, right now I want you to assume that everybody has the same algorithm. If I'm influenced 0.1, so are you. We'll use, if you want to use a Gaussian, that's fine. But we have to use the same. This is very important. Because that means that the graph will be directed. Would be undirected. It will be a symmetric communication, okay? And this is very important. So now the algorithm is you move to the mass center of your neighbors, or maybe you put some weights as you suggested. You can put weights, that's fine. But you but archetypically you move to the mass center of your neighbors. And everybody does that together, and you just keep on doing this forever.
So your neighbors is within a radius 0.1.
Exactly.
So
yes.
if I move, will I never lose some neighbors by 2? I mean, I move
Yeah.
to the center and then
Yes, anything can
somebody
happen.
on the side
Yeah,
side
so,
moves.
all right, so in one dimension, nobody can take over anybody else. But that is because it's one dimension. In two dimensions and higher, anything can happen. Literally anything can happen because there could be a coalition of people that try to influence you, and basically they can write your behavior they want from you, and they can program themselves to influence the world so that you follow exactly that behavior. But not in one dimension, that's impossible. But in two dimensions and higher, it's arbitrarily complex, the phenomenon that you can have. So, so this is a sort of typical face portrait of this. And there are variations on the model where maybe you pick two random agents. And if they are far apart, you abandon them. But I mean, you just move on. If they're close, then you apply that. So there are all sorts of variants, but they all produce similar pictures. There's bifurcation. And eventually, so this would be in 3 dimensions. Now, what Lawrence showed in 2003, is all these systems eventually converge. They not just converge, they actually freeze. And Martinez et al. Proved a time bound in dimension 1. And I showed an exponential bound in any dimension, which is almost certainly not optimal. I suspect there is a polynomial bound, but I don't know how to prove it. But this works in any dimension. Dimension 1, as I say, is much simpler because all sorts of behaviors are forbidden. It simply cannot happen. Now there's a variant of this, which I like very much, by Kurtz and Rambau, in the field they've invented, they call social epistemology, and which basically means what it says, that is how do you acquire knowledge? By, say you're a researcher, you acquire knowledge by thinking hard, by talking to your friends and colleagues, and by reading papers and writing papers. So there's this sphere of influence, and maybe you read things that are false, but you think they're right, so you get influenced the wrong way, and so on. So one of the questions was, if you know that the truth, whatever the truth is, that you're exposed to it, at least in a recurrent fashion, will it be true that you will eventually, snap on it? And so I showed this is true, indeed the case. So I'm just showing you results right now, okay? I'm going to then switch
So
and show you about.
You're using a similar proof, so it could take you a very long time to get to the
It could take exponential time, yes.
So I have a question on that. So how is that related to the fact that sort of the Bayesian machine learning, people argue that eventually you can't agree to disagree. We all eventually.
Yeah, that's a Kahneman thing. So that's a very interesting. The system I'm presenting here are inherently non-Bayesian because you do not really adjust your belief on distributions. You do not maintain a distribution of beliefs. You actually maintain a scalar value. This is my belief, this is yours, and so on. So, needless to say, people have looked at the Bayesian version of it. Some economists and some computer scientists and so on. And so I'm not in a position to tell you really. I mean, maybe some of these results apply and maybe not. I really cannot make some statements. But I think this is economists in particular will argue that this is more natural. That's the way it should be looked at from a Bayesian standpoint. Yeah.
So I have a question. So essentially, you take these phenomena, you model them mathematically, and then you prove results.
Yes.
So how My problem is in the modeling. How do you know that you modeled it correctly?
Yeah, that's a huge problem. Yeah, that's a number one problem that I mentioned that I said that I would skip. So, I mean, there's the Weasley answer. I mean, sure. I mean, you do validation. I mean, for natural sciences, they always do that. They come up with a model and then they try to validate it. But you're right. I mean, there could be overfitting where am I proving something about the model or about the phenomenon?
Exactly.
That is the fundamental question. So I have no answer for this because I think that's really is. I mean, at some point, like in all of applied sciences, you make predictions about the model, and then you see whether in the lab you actually find that.
But like in your results, is it like, did you make up the models or you?
No, I did not make up the model, but some human being made up the model
Okay, yeah.
based
Okay,
on
I see.
observation.
I see.
Yeah.
So they did the observation, you did the proofs.
Yeah, no, I did not come up with this model. They came up with a model, and I mean, I should give them credit. They actually do a lot of empirical studies. So, I mean, I'm not equipped to improve on the model because simply it would have, you have to be a sociologist or something and do those things. So I have to take the model as they give it to me. In particular, the Bayesian one, I think now is very hot. But still, even if they know what they're doing, and let's hope they do, I think you're raising a fundamental question, which I think maybe we can come back later. Yeah, I know.
Bernard,
Yeah, yeah.
Once we raise this question, so are you proving this converge? Like, how fast does it take
Yes.
to whatever
Yes.
blocks to converge? Is that sort of observable in some real life setting? Is that part of what the scientists need in order to validate such a model is an observable consequence, and then they want to see whether that happens
Yes.
in real life.
Yes.
Is what you're doing is producing one of those consequences?
Yeah, so my comment, brief comment, will be not for agreement systems simply because I do not believe my results are optimal anyway, even theoretically. I think these are polynomial, they should not be exponential. So my bunny is wrong. And so, I mean, it's not wrong, but it's not optimal. I don't believe it is. So I don't expect to see it thing. On the other hand, it's based on results I will mention later, which are provably optimal, and therefore, and these can be observed. These are convergence of Markov chain-like results. And the third thing I want to say is that convergence is not a terribly interesting problem. And so why don't like prediction is really the interesting problem. Like flux, I want to know whether I end up with one flux or more than one. Can I flip a coin, or I mean, is there a better way of knowing? You want to know, will it eventually have one flock or more? The prediction questions are much more interesting. But the reason why I'm not working on them is because I think I'm doing the right thing in the ordering, that I'm working on the questions that are less interesting. But I think there are, it's like a very complicated stuff. I have no clue how to do prediction. So I'm really doing the convergence aspect of it because I think that's where we can connect known tools that we can use to real questions. And even if the questions themselves are not terribly interesting, the hope, so in the process, you build tools. The title of this talk was not results on, it was tools. So the hope is really that at the end of the day, I don't think the results are interesting, is that hopefully the tools that are built in the process, and I want to show some tools now, so that maybe you haven't seen. Well, I hope you haven't seen them because, well, okay. Oh, I'm sorry, yes.
In the first case, you said that the results are optimal in the sense of convergence time. Yeah. And so if we believe that birds are simple computers,
Yes.
and if we see the flaws,
Yes.
then maybe the model is wrong.
Yeah, maybe not. These are worst case results. This is a worst case result, and so the answer could simply be it's irrelevant because birds do not do worst case, which would be fine with me. It could also be the model is fundamentally wrong. Now, let me briefly say something about the model. Something really one of the most amazing things. Before Vishek, Vishek, Smale, and Cooker were kind of, but before that, there was Reynolds, who invented like virtual reality. And he's the one who came up with the basic rules of flocking, of flying. These rules are used in all computer animation in Hollywood, Pixar and so on. Whenever they have birds flying, that's what they use. And I've seen these animations, and they are stunning in the sense that sometimes I'm not sure if I'm seeing real birds or animations. Now, Jennifer is eating an apple. Now, this is okay. I'm not blaming you. But in computer graphics, the ability to draw an apple that looks, no, I had one, thank you, but I appreciate the offer. To draw an apple that looks like an apple took about 40 years of research. I mean, this is a cutting-edge research to produce an apple that actually looks like an apple. So it was very difficult. It took a lot, but for flocking, what is really amazing is why these 2 or 3 very simple rules, when you implement them, they produce incredibly fabulous results. Now, why is that so? Maybe there's something scientific behind that coincidence, or maybe just a coincidence we lucked out. But I doubt it. I suspect there's something fundamental in the fact that these rules suffice to give this visual impression that is virtually indistinguishable. Now, it's for us. Maybe if a bird saw the video, they would be laughing. So you're like, ha, yeah, right. You know, it's like us looking at sticks, human sticks, and somebody say, oh, it looks just like you. You know. Okay, so let me talk about some mathematical modeling of this. There's something in common to all these results, and I want to talk about this. So now, okay, maybe forget what I've just said. Now we'll reconnect later. So here's a problem. Here's an arbitrary sequence of graphs. So again, the word arbitrary is in red because this is important. Every time I say this, there's always somebody who says, but what do you assume about the graphs? Let me make it clear. I don't assume anything. They're completely arbitrary. And
but n is fixed.
yes, n is fixed, yes. And Michael Fisher, the statistical mechanic, when I said that answer, he said, what do you mean by arbitrary? So then I was taken aback. So yeah, like arbitrary means free will, probably means the existence of God. So, whoa, this is a tough question. You know, arbitrary. So you take another arbitrary embedding. So you take your first graph, G0, and you embed it in space of your favorite dimension. Arbitrary, okay? No assumption whatsoever. And now I'm going to define a dynamical system, which would be non-deterministic in the sense that the rules will have lots of freedom. You can imagine a little adversary there, a little devil that just simply decides what to do at every step. It's, you could make it deterministic if you want. You can make it probabilistic if you want. But it's more general than that. You can make pretty much anything you want. But there's some rules that you have to follow. So the graphs are given. But what is not given will be the embedding. You have the first embedding, but you don't have the others. Now, I will tell you how to produce the others. There's a rule you have to follow, and here's the rule. Now, you are at G0, and it's embedded for you. That's part of the input. Now, you want to produce the second embedding. How do you do that? Well, for each node, you will perform the following task and repeat that task for all the nodes independently, okay? You can do it different ways. But so you pick the node, and then you look at its neighbors, and then you take the convex hull, which you can, you're in Euclidean space. And now you shrink this by tiny factor 1 minus rho. Think of rho as a 1%. It's arbitrarily small number that you can pick, but it should not be 0, very important. So you shrink it a tiny bit, and then here's what you do. You take the node and you move it within the convex hull anywhere. That's the non-deterministic part. You can move it absolutely anywhere you want. Okay? You can solve the Riemann's hypothesis and from the length of the proof. That will tell you where to move. I don't care, any way you want. And you repeat this for all the nodes. If you knew how long it took me to do this PowerPoint, I hope you appreciate this slide. And then you repeat. This goes on forever.
Using the same rule?
No, well, yes, they use the same rule, but the motion is completely independent. So this one will move inside its convex hull, but anywhere it wants. It does not have to know what happened here. They're completely independent.
But there's a rule for how to move. It could be I move uniformly or
No, there's
every
only
one of them can use a different
right,
rule.
exactly.
Okay.
So maybe you're right. I should not use the word rule. There's no rule. They are prohibition. You have to move inside the convex hull. That's the only. This is a constraint.
Now, when you say independent, what does that mean?
Yeah, that's not a good word. I agree. They do it not. They don't have to know what the other is doing.
But they could know.
They could know. They could be dependent. They could all move exactly the same way.
And it could be a function of...
Yeah, they use free will, and they do it in an arbitrary way.
To use only does it have to be
Markovian?
Yes.
Yes. They have to, well, they only have to know about themselves, what they are. That's the Markovian part. Right.
Can they be a function of GT plus 1, GT plus 2, and so on?
And a function of the current graph. Yes.
And
But
your
since
nodes
it's
are
arbitrary, it
labeled.
does not even have to be a function. You see
The
what I
nodes
mean?
are labeled.
Yeah.
The nodes are labeled, yes. Yes, they are labeled. Every agent has a name. Every bird has a name, yes. So, and so on. And this goes on forever. So this never ends because this sequence is infinite. Okay, this never ends. But this video will end. Now, just to make sure we understand, yeah,
So how do you decide in the next sequence who are the connected and who are not connected?
the graphs are arbitrary.
Given.
You see, the word arbitrary really, really simplified, very tough to. So give me any sequence you want. You don't have to give it to me ahead of time. You can say, I'll just decide as we go. That's fine.
So the graphs keep changing from iteration?
Oh, yeah, should change. Yeah, it's more fun to change. You can change anything you want. You're just not allowed to add more agents.
But at time t, I'm not allowed to use what happened at time t minus 2.
Yeah, you can, if you want.
But I can't use the future.
This is becoming very philosophical or
Can the
theological.
movement of the graphs, the embedding from t to t
Yes.
plus 1, depend on how the graph looks at time t plus 5?
Yes, it could depend on the entire sequence of infinite graphs. You could have that if you want. Yes, yes. Anything is acceptable as long as you stay within the convex hull of your given graph. So the only thing you need to know is the given graph, is the current graph. And it doesn't matter whatever else happens, right?
So there's a for all quantifier on
Yeah, for
the
all.
choice on the graphs and the moves.
Yes. Maybe a better use than arbitrary, a better word is for all. Yes. Oh, maybe those mathematicians were onto something when they invented logic.
They must have done something right.
There was no that. So again, any graph sequence, any initial embedding, and any moves within the perturbed convex hull. Are we clear? Now, if you think dually, which you will want to do, for a second I'll tell you why, you should think of this. It's really equivalent to doing a random walk, and I mean random in this case, over a graph that changes at every step. So just imagine, instead of doing a random walk on a fixed graph, the way we usually do it, every step, there's a new graph that comes. But it's still the same set of nodes, so your node doesn't go away. You're still on the node, but there's a new graph, and there's a new graph. We call these colored random walks in computer science. And so this is the dual way of looking at this. We'll see this when we look at the transition matrices. I just mentioned this just to say, in order to make statements about this, you have to build a theory that will therefore subsume all of Markov chain theory as a subcase. I mean, you have to do that because this will contain this as a special case.
So there's a non-deterministic aspect of this random walk as well, right? Because your location is going to be in the 1 minus row of your convex hull of your neighbors.
Yes.
So sort of the update function.
Yes.
You can now choose anything.
No, so the 1 minus rho condition in the case of random walks will be that transition probabilities cannot be too small. They can be 0. They're low bounded by rho, basically.
Right, but that only gives you a feasible space of what your new update is in that vector. It doesn't define it, right?
Yes, I guess so. Yeah.
That's why he said
Let me just postpone this. I'm sure the next slides will clarify what you're saying. Okay, I'm quite confident. So, and if it does not, please let me know. So I want to introduce this new tool, which I think is useful, which I call the total S energy, E of S. Let me define it. Okay, it's a generating function, and I'll show you why it's useful. So here's what you do. I will define this this function, which will, and I'll show you why, it encodes all the length of the edges over all of history, okay? And here's the way I do it. So this is a double sum. So for all times 0, times, and so on, I look at graph GT. This is GT. And I look at the distance between all pairs of nodes that are adjacent. And I take some power S. I take the L2 norm, and I take some power S, which is a parameter. And I just sum all that like crazy. This is it. Okay, then what can we say about this? Does it converge? Probably not.
So you got like, I could think of this as springs or something.
Exactly. Yeah, in fact, that's a very good analogy because in the L2 world, you can look at this in an outgrowth of the
So this is like my coupling.
of the Laplacian. Yeah,
Right.
exactly. So if you look at this and you remove that and you transform S into a 2,
Right.
you see this? So this is simply the positive semi-definite form that comes from the Laplacian of the graph. So what you do is you replace 2 by s, and you sum over all. Okay. All right.
S is larger than 2 or
What?
smaller? Do you think of S as larger than 2 or smaller than 2?
I'll get to this.
Is S complex?
Yes, but we'll get to this. So, but right now, I don't think of as
Oh, so you can
complex.
have damping.
Yeah, you can have damping if you want. Okay, so this is E of S. Let's see what we can say about E of S and why this is useful. Okay. But first of all, it does not always converge. For example, when S is 0, this is the number of edges over all graphs. It's most likely infinite. Okay, so, however, I can show the following: that if S equals 1, this is always bounded by this function, and if S is between 0 and 1, it's bounded by that. Now, this n squared, I believe, should be n. So if you want to work on this, please try to improve this, because I don't believe this is. But this is optimal. But this one is optimal. So in that sense, that. Okay.
So you assume that the 0.0 what?
Yeah, so
they're
is there a-
only being
What?
Is there a constant E0 in front? Or, sorry,
normalization function.
yeah. If I just double the distances at the beginning.
Oh yes. Sorry. Yes. Of
Yeah.
course. Everything is inside the unit
Unit.
box. Yes.
Right, the unit,
Yeah.
yeah.
Exactly, yes. So pursuing the Markov chain analogy, you could ask, well, is there such a thing as a reversible agreement system? You know the notion of reversibility in Markov chains is very important.
Back up a bit. Are you going to tell us anything about the proof of this kind of a thing?
I will, this is not part of the talk. Well, you said I shouldn't give a technical
S
talk.
greater than 1?
I will talk about this, about S more. I'll talk more about it, but I'm not going to give proof. Okay? So if it's reversible, and again, I'm not going to define what it is for this to be reversible, but I think it's interesting because it gives you a geometric understanding of reversibility. Reversibility, is defined typically by some balance condition that involve a stationary distribution. So you have to know the stationary distribution. But you can actually define reversibility as a geometric condition. Remember, like you move within the convex hull, so you will move not just within the convex hull, you have to move according to stricter rules. And that will impose reversibility. And you will notice that when this happens, and this is the right definition, by the way, this will also subsume reversible Markov chain as a result. So you see that the S energy becomes very different. You get this bound for reversible system, which is optimal. And from this, you rediscover the typical mixing bounds on arbitrary reversible Markov chains. It's polynomial versus exponential, which you would expect. Because, reversible really implies that it's diagonalizable. And if you have the right condition on top of that, then you have polynomial bounds on the walk. Yeah.
Can I try to understand these results? I mean, are they trying to say that all the points will eventually converge
Yes.
to the same?
No, not to the same. All the points will at some point stop moving. That's what they said. Not completely stop, but visually speaking, they will stop moving most likely into clusters. So if they all move together into one cluster, that's consensus. That's what we call consensus, and that's good. But it does not have to be. It could be that they will, because this implies convergence of agreement system. But that also has a philosophical
So is rho something
issue.
like a uniform number in a Perron-Frobenius theorem or something like that?
Yeah, you can look at it. Yeah, that's a very good way to look at it. Yes,
Sort of a damping factor, right?
It's a
I mean,
uniform
saying-
bound, and okay, actually, it does not have to be uniform. I could change rho, but let's stick to this. Yes, exactly. Yeah. However, the proof has nothing to do with Perron-Frobenius. I mean, that's the whole point, in fact, that algebra does not work, and so that's now. Let's see.
Can you tell
yeah.
us what field you use for the proof?
Oh, yeah, computer science.
Computer geometry.
Geometry or?
Yeah, combinatorics and geometry, and yes.
So not analysis.
Yeah, no analysis, but more important, no linear algebra, because this is really what kills you when you lose reversibility. Linear algebra becomes useless, even though there are matrices, but so what? When you multiply matrices that do not commute, good luck. But something else I wanted to say, which is kind of philosophical, because when people say, but this cannot converge, you're lying to me. Because just imagine that you have n over 2 here, n over 2 there. This n over 2 converge and these enough to converge, and arbitrarily long time in the future, these two guys decide to communicate. Nothing prevents this in the model. Geez, the graph is arbitrary. So I will say, well, wait until that happens. And then, you see, when that happens, then the two guys will start coming. But there's no bound on how long this will take. So this cannot infer a bound on how long it'll take for conversions because there is no such bound. After all, an adversary can always delay this connecting edge forever, absolutely forever. So it's really a quantifier kind of thing. Yeah.
But does that mean that sort of limit these quantities are finite? Everything will converge to 1 point?
No. No, so I'm glad you asked this because it doesn't sound, you would like to say if you do analysis, that if you wait long enough, these converge, get smaller. That's the whole point, but they don't here. You cannot put a bound. I mean, this edge that would connect Cambridge and Boston, I could, imagine Cambridge having gone to 1 point and Boston into 1 point. That edge connecting the two, I can delay arbitrarily. There is you cannot say, you cannot quantify this ahead of time.
Can you think of the energy as being a budget for how much movement?
Yeah, well, so actually that's how the proof goes. Okay. The proof is very much the sort of Tarjan-like arguments of passing credits around, because this is all about message passing, and each message carries a bit of energy, and sort of pass it around and so on. So let's look at, now I'll address some of your questions. Maybe I should reverse some of the slides. If you look at this generating function as an analytical object, maybe you can make some statements. For example, the first statement you can make is, don't hope to resolve the entire thing. If you take a very simple graph that has only 2 nodes that are connected, the graph never changes. But let's say that the distance is 1 over t. You couldn't get this in agreement systems, but you could get this in the model that I described for the S energy. And the S energy would be the Riemann zeta function. So clearly, it's not going to be, this is the simplest possible case you can imagine, so these objects are not necessarily simple. However, you can make some statements. You can, there are so-called generalized Dirichlet series, and they have an inverse formula that you can inverse those things, Laplace transform, which means they are really generating function. I'm not using the word in a sort of because it sounds good. They really encode exactly all the edges, precisely, not approximations of them. It's a lossless encoding. And here's analytically what you can say. So when I show this is finite for all S positive, and you can show easily it's analytic over the complex plane, as long as you move a little bit away from the imaginary axis. Another question that you would ask in the spirit of the zeta function is whether you can continue this function. So in general, no, you cannot. I mean, it's not deterministic. There's no way you could continue this in general. But I conjecture that the system that achieves the maximum value has an analytic continuation. I worked it out for 2, which is simple. And you get this lovely. So this is the total S energy of the maximum system of 2 nodes. And it's continued over, I mean, it has an infinite but countable number of poles along the imaginary axis. And why is that useful? It's useful because it's a generating function, and the reason we like generating functions is because they provide Chernoff-like bounds on all sorts of quantities. You can measure tails very accurately. So from this, you can, in particular, infer that all agreement systems will converge, regardless of graph sequences, regardless of motion choices, and you can actually, once you make further assumptions, as you can in the case of bird flocking and so on, where it's not even probabilistic, it's deterministic, then you can actually get bounds on the time. Now, the intuition not on the proof, but why the total S energy is fundamentally different from the current technology. So, I mean, I assume you know a little bit. I know some of you are experts about stochastic matrices. So we're looking at it as a product of stochastic matrices. And when I say the dual versus primal, is I'm looking at it from the right to the left. If you do a random walk, you look at it from the left to the right, but that's pretty much all we're talking. This is the only difference. Now, let me suggest the following way of looking at a matrix, a stochastic matrix. Look at a row and look at this as a point in 4 dimensions. All right? And so each row has a point, so you have 4 points. Take the convex hull. Now do this in any dimension. So you get a polytope. Okay? Now, when you multiply 2 stochastic matrices, here's what happens. You get a smaller, so now each matrix is associated with a polytope. But when you multiply, the action of this group on these polytopes, on these matrices, produces smaller polytopes, produces polytopes. And they're smaller, so you can prove that whenever you multiply this by this polytope can fit perfectly inside. This is linear algebra, okay? And trust me, but I believe all the proofs that are known, and until somebody contradicts me, about convergence of random walks, of Markov chains, of just all of that, try to do the following. They try to show that these polytopes are shrinking. Even though they never mention the polytope, almost never, they're really trying to measure this polytope is shrinking step after step. Now, a polytope can shrink in many ways. The diameter could shrink, the volume would shrink. So these are what's called coefficients of ergodicity, and you could have the spectral gap, which is an L2 average of how big this polytope is, the diameter, the volume, the width. There's whole literature on all these things, but each of them tries in its own way to tell you when you go from here to here, things shrink a little bit. And the S energy is fundamentally different. It's not a local approach. It doesn't care where you go from here to here. It could be for a long time you make no progress. But it looks at these trajectories over this parameter S. So it looks at a different space altogether and tries to achieve the shrinking over this enlarged space. That's the advantage of using this function as opposed to the other. That was the intuition. It's not a proof.
So in the analysis in general, you need to know about the entire S energy profile to analyze the convergence?
That's interesting.
So for FDS?
Yes. In fact, yes. Yes. Correct. So in fact, the proof itself, if you try to think of it chronologically, you go to infinity and then you continue. Yes. Yes. No, that's true. Yeah. It's a little strange. Yes. In fact, the lower bound, because some of these bounds are optimal, and the lower bound does that. There's a system which goes, and then you wait to infinity. And once you reach infinity, you start the other one. I know it sounds a little strange, but. So let's take stock we've done. I mean, many ways we've done the easy case. We talk about bird flocking and firefly and this. But all we've done is to say that the face portrait of these animals are very nice. They just have, there's some kind of potential function, the S energy, and in front of, say something about it analytically. But the point is that eventually each one will converge, will fall into some kind of sync and just go boom, all of them. The dynamical systems don't have to have this nice property. In other words, there are attractors, there's an attractor set, and the basin of attraction is the entire phase space, which is kind of lucky.
So you're saying there's a global? This doesn't look like a global.
No. What I meant to say is that everybody converges. Everywhere you start.
Oh, everybody is attracted to some.
To somebody, but they could be different. Yes.
Right.
They will be different. Yes.
So there isn't anybody.
I'm getting to this now. Yes. So the fundamental, what all these have in common is that the networks are undirected. Now, realistically, this might be stupid to say this because when a bird is following you, the bird might see you, but you might not see the bird if I go behind. So to say it's symmetric doesn't make any sense, maybe, or maybe it does, I don't know. So is symmetry important? And the answer is yes. So I want to get to this. Well, first of all, when now you say, what if the GTs, these networks, are directed? Is it really different? It's fundamentally different. It's universal. I mean, even something like this, basically you can embed a Turing machine. This will, it will not just oscillate.
So
you're going
to get your non-reversibility somehow in this more general one?
Yeah, but this is even much worse than non-reversibility.
Yes, obviously. But it's like a generalization of non-reversibility.
Absolutely. Exactly. That's one step further.
Right.
So now, maybe a quick digression, because I think this is relevant. If you take Markov chains, I mean a random walk on a graph that is undirected, which is the simplest case, like an expander or something like that, okay? You have all kinds of nice properties, like reversibility, because it is undirected, okay? Now, if you take undirected graphs, which are different, and you take this random walk over each one, so it changes over time, even though each graph independently, separately, is undirected, you can emulate the behavior of a random walk in a directed graph.
Because time is giving
Yes.
you direction in one higher
So that's something
dimension.
that Condon and Lipton and others showed years ago. So even though each graph is undirected, because you change over time, you can in effect, all the bad things about directedness will come back to haunt you. Here, it's even one step further because at each step they are undirected. And now you get universality. I mean, it's well known that affine, these are piecewise affine dynamical systems. And you can embed Turing machines with those things. I mean, neural networks is a good example. They're not linear, but they're almost linear. And
Now I don't understand, because your previous networks,
Yes.
before you put these edges here, this directed,
yes.
they were undirected, but you had time.
Yes.
So therefore they were universal, and as a Turing machine might never hold, so how come you can have bounds?
Now, in the previous case, the system will eventually stop. No matter what you do, at some point you will have clusters, and the clusters will only get smaller and smaller. I mean, that's a fact. So you cannot get universality there because, because there's nothing to see after a while. If it's directed, then
I see. So it's not
it's
true
totally
that
different.
if you do undirect, yes, you have some direction, but it's not the universal directed graph you
Yes.
get.
Right. So non-deterministic must go. So let's define asymmetric
Quick question.
agreement systems. Yes.
Have you also considered sort of a mixture of directed and undirected? Sort of how much direction is needed to mess it up?
Yeah. So it's very interesting you mentioned this. So I mentioned briefly this result on truth seeking, the Kurtz-Rambaugh thing, where how hard is it to find the truth if you're exposed? Now the proof of that relies exactly on what you're describing. Everybody is symmetric, is undirected, except the truth. The truth is directed. And the reason is the truth is never influenced by anybody. So there's no edges from the truth to anybody, but there are edges from people to the truth. And that's what got me to the more general case, which is, well, we might as well then just simply, you never lose anything by assuming directedness, because after all, you can put two edges going, and so. Yeah. Now, so here's what we'll assume. That here's the model of the graph now. At any time you have a graph which is completely arbitrary, well, yes and no, not quite. Is there an edge between I and j, you want to know, at time t? Well, the pair ij has a formula, a first order formula phi of ij. And you plug in their position at time t, and they'll tell you yes or no whether there's an edge. This is not symmetric. Fij, Fji are different. I mean, they could be different.
But this is like a generalization of your influence
Exactly.
regions.
Exactly.
Yeah.
It's a generalization of except it's no longer, this is now this is deterministic because the graph basically is no longer arbitrary. I mean, this is maybe arbitrary, but still, this does not change over time. The formula does not change over time.
xi is just some arbitrary x you just created.
It's a position. So this is,
Oh, that's a position of your embedding?
that's the position in the embedding, exactly. That's the position of h at I.
So
That's
So
where it
is
is.
there an edge? So sometimes there is, and then after a step, when they randomize in the, or do whatever in
Yes.
the 1 minus row
Yes.
neighborhood, they might not be
So,
connected next.
so for example,
How is that a generalization of what you did before?
because,
Or it could not depend on the axis? For
yes,
example.
yes, yeah, right. But for example, phi could be distance. If these two guys are within distance 1, say yes. But it does not have to be, yeah.
Is phi not symmetric but co-symmetric? So
No.
if you change x,
No.
I and xj and I and j,
No,
it's the same?
no, there's no symmetry at all. There could be like decision trees, totally independent
Any
decisions.
assumptions on phi?
No.
Because it seems that they're totally arbitrary, then
Yeah, okay,
Then you can encode a
yes,
directed
yes,
graph.
you're
How
right.
do you prevent
You're right.
encoding a directed graph?
Think of a-
Why?
I'm sorry, I'm trying to answer to, think of a decision tree, maybe it's easier, where you have, let's say, hyperplanes and maybe nice polynomials or something. But yeah, no, this is not completely arbitrary, you're right. Yeah, it's the sort of, like a real algebraic, logic, style, the Tarski sense. Yeah, you say
So how
something.
do you prevent, so phi could not depend on the axis,
Me-
and then
Yeah,
could
right.
just encode a directed graph, which you didn't want me to do.
No, it can encode directed graphs, but
Yeah.
not all directed graphs or something.
Yeah, you're right. I don't know. You're right. No, this would be very restrictive. Now, the GIs are no longer arbitrary. The GTs are no longer arbitrary. What's arbitrary is phi. But once you've decided phi,
Then
Phi
it
is not a function
produces
of
G
T.
for you.
it produces G for you.
Right.
Exactly.
It tells you whether they're neighbors
Yeah,
or not.
and you're going to get not every G. Yes,
Right.
that's right.
So
But
this
and
is a
yes,
real,
I make sure that I have. Yeah.
This is
it's
the
not.
thing which will tell you things like whether the graphs will merge
It's
or not.
connected.
Yes,
Not.
yeah. So like in the social, in political opinions, it would be if Madhu is within 0.1 on cultural issues and further than 0.3 on economic issues and blah 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 blah. There's some formula. Then we have an edge or something, and yeah. So the transition matrix looks like this. You have a 1 or a 0 divided by the degree. I mean, the
Oh, and
standard.
you have only a certain amount of influence, like
Yes.
Laplacian, so you can only put out your influence to, your influence is diluted by the number of neighbors as
Yes.
a random walk or a Laplacian
Exactly.
would be.
Exactly. Yes. Yeah.
Okay.
So I show that those guys are generically asymptotically periodic, and they are. I mean, you can come up with
Instead of everybody falling into a
yes.
minimum,
You can come up with what Jennifer was suggesting, that actually things do not have to converge. They can just go oscillate forever. I mean, you might think at first there must be some kind of conservation, but no, right? It could be the divergence is 0 or something. It's there's no curl, but no, that's not true. So it's very different from the previous picture.
So when you say agreement systems, these are the ones with the first order logic
Yes.
formula?
Yeah. Yes.
Okay.
By asymmetric, that's what I meant. Yeah. So. So here's what will happen. They'll start moving around, and eventually some will stop, and the others will continue forever, and eventually they will become periodic. Not perfectly periodic, asymptotic. In other words, there's a limit cycle that's periodic, but they get closer and closer and closer. But maybe they never touch it. And now, those guys here, okay, there's just one here, but actually you could have a whole cluster going, shrinking to 0. That's possible. Other factoid, you cannot have only one of these guys and be periodic. That's impossible.
So how are they
Okay,
leading?
and that's why the truth wins, by the way, because the truth model is something where you have only one. And this theorem says that actually you cannot have a periodic system when you have the truth.
so is that like some kind of source or sink, or is
Yes,
it
yes. I will say more about it.
What is the convex hull?
What?
You don't have to shrink the convex
Yeah, so I think I'll talk about this. Okay.
But
yeah.
did you relax that restriction that you have to stay within the convex hull? Or it's
No.
It's still there.
But let's say that the vertices on the convex hull never change, never move.
But they were not in the picture.
No, suppose that there is no outgoing edges.
So it's directed.
If there's no outgoing edge from
There's
you,
some pins,
you
then
you never change because you're never
the
influenced by
truth
anybody.
is
Is you.
eternal.
You are the truth. You're eternal. Why would you change? Suppose everybody has that opinion of themselves, and they're on the convex hull. It never shrinks. Inside, they're being pulled apart by all these gods who pretend they have the truth, and they refuse to change, and they can bounce. So this is kind of interesting here because what it says is that if everybody has the same influence, then this will always converge. On the other hand, if you have different influences, you can fall into cycles. I don't know if there's a common sense interpretation of this, where people might say, yeah, I know that when you see kids in the schoolyard, and there's a bully, and there's these people are very confident, they're never influenced by anybody, and some others were extremely influenced, and
So
you can
the
have
entire
cycles.
system, I mean, if you start with a collection of points, you always stay within the convex hull of that collection of
Yes,
points,
that-
right?
that is
I mean,
true.
So
That is true, yes.
Okay, so in this picture we had these guys going off to infinity. That's because there are other people
No,
that we didn't see.
nobody is going off to infinity.
The corner of the screen.
Yeah.
yeah,
You're
right.
right. This picture is wrong.
Oh, all right, sorry.
Touche.
Okay, no.
Touche. Yeah, you're right. Actually, those guys should be moved.
Yeah,
Right.
Moved
yeah,
here.
yeah.
Yeah,
Some
right.
people
Oh,
that we
my
didn't
God.
see.
Sorry. I apologize.
See, he is listening. Huh?
No. Amir is
No.
Amir is
I'm
listening.
interpreting.
Yeah.
I don't quite understand how it can be periodic if at every move you can go anywhere within the convex.
No, you cannot go anywhere.
Oh.
because now there's this fixed first order logic
Got it.
graph. So yeah, otherwise, right.
Again, in first order, you mean comparisons and arithmetics?
Yes,
so it's
and the
only-
arithmetic is going to have to be bounded because otherwise you can encode. I mean, I don't allow you to transcendental
First order
functions
theory
and
of
so on. The first order theory of the reals. That's what I was looking for. The first order theory of the reals, exactly. The ideas for this is renormalization, total S energy,
That's
which
why
you
you were
see.
telling Michael Fisher about
Yeah, I'm not sure he.
bought it.
What do you mean by renormalization?
Okay.
Do you mean real space renormalization, or do you mean?
No, so I mean something. I'm just borrowing the word because I love it. And there is a relation, but not one that purists like you would accept. I'm not sure one Fisher would accept, but I believe though, and maybe if I have a few minutes, I'll say this. I'm almost done with the slide, so we can open this discussion. But let me just briefly talk about this and then come back to that. So actually, a quick sketch of the proof. Why is this thing? The first thing to look at is communication. Who communicates to whom and who influences whom? Take a cut. And either or the following is true. There exists a two-way, for every cut, okay, there's a two-way flow of information back and forth at any time. Either that's true or false. I mean, this is, now, here, suppose that, now let me enlarge this statement by saying, suppose that there exists a time interval t, which is unknown. There exists t. Such that if you take the union of all these graphs over the time t, this is true. So this would not have.
And I'm identifying them because my particles are identified. For
Yes,
one
exactly.
stage.
They're labeled, so you know who is who. And let's assume they don't happen at the same time, but they happen within an interval of time t that is unknown. Okay. Now what I will do, I will renormalize time. I'm going to take time. I will renormalize time by this unknown quantity t, to simply assume that what I want to argue is the following: if you ever talk to Christian, then you will do it right now, or maybe tomorrow, in the next step. See this statement? I mean, maybe you never talk to him again, but if you do, I want you to do it like this next instant. So I think this logical step, because
So wait,
this
if
way
you ever
I can.
do it in this interval, then you do it this instant.
Yeah, but since the interval is anything, the interval is arbitrary. I will actually say, if you ever do it, you do it right now.
But if I do an
It's-
arbitrary rescaling,
No,
I can
it's
just be.
yes, yeah, but this is finite. I mean, there's a finite number of agents, so
Do you do that?
I mean, so
You have to do that
Well, everything
synchronous
is
for all
finite.
yeah, I mean,
Yes,
a number
everything's
is finite or
finite.
infinite, so I can
Everything's
decide
finite.
whether it's. What?
You have to do it synchronous for all vertices.
Yes, yes. So the renormalization will say, I don't know what that interval is, but if there is such an interval, let's just call it 1. I mean, it's just I changed the unit of time. So it just simplifies things a lot. And this will have a recursive structure, you will see, because, so if that happens, then there are several cases. Either at some point there's no flow, in which case these are independent, and I can solve them recursively independently. Or there's flow on both ways, in which case what I will do, I will try to see how the information propagates from left to right. And these are two-way flows for which the total S energy works nicely, okay? But what will happen here is when you get to here, then the whole thing will shrink. I thought I had a picture of this. Oh, I apologize. I had a picture and something happened. The whole thing will shrink. You know, like the convex hull, somebody said, but doesn't the convex hull always shrink? If you have a lot of two-way communication all the time, the convex hull will shrink. So then when you trigger, there's a power law that kicks in. So then, anyway, you can write some kind of recursive formula, assuming renormalization, where you have, this is the message passing business that goes on, and here there's a power law that kicks in because
So wait, this
things
is
shrink.
the guys across the boundary, or what's going?
Yes,
what's this
exactly.
term?
This is the time it takes for all the energy to propagate on the left of that yellow line and the right, and then you sum up.
And the right,
over
and
the-
that guy's the boundary.
Yes,
term.
exactly, yes.
And that's why the coupling or the oscillation or
Yes.
whatever is coming in.
Now, if these two-way things were to happen recurrently like this, now, to some extent it's an easy case. You would not have periodicity. The tough case is, what if there's a one-way flow forever? Okay, so it might as well happen right now, But they will never, B will never talk to A. Let's assume that. I mean, that's possible. So here's what happened. Now you can define some kind of semi-group structure over this where you split the dynamical system into two parts. One is kind of symmetric and you can use total S energy tools. And the other is where the periodicity is confined. And that, once you define it, you have to look at the bifurcation space. And that's where you use space partitioning. So here's the problem. So this is a step that in algorithms we don't do enough, I think. But this is bread and butter of dynamical system theory, which is that when you look at a trajectory or an orbit of an algorithm, in computer science we say, what's the worst case? So this is the worst case. What's the average over everything? But people in dynamics very often will do something else. They will say, well, let's start from a tiny little ball around an arbitrary point, and then let's just follow this ball and see what happens to it. And maybe there'll be bifurcations because it hits something where there are two possibilities. And so now, if this thing moves like this and never lands on these constraints, okay? So what are these yellow things? This would be where the first order sentence is true on this side and false on the other side. This is where something happens,
Oh, so if
actually.
it lands and it has to bifurcate.
So if it lands in here, then it bifurcates. And then you get more. And this can go on, and this is where all the work is, to prove that it's not chaotic. Because chaotic means that this basically can go on forever. To prove that it's not chaotic, then you have to use the fact that it's secretly dissipative. If you project it in the right space, the whole thing is not dissipative, but it really is.
Whether S is, if S is complex, then it is dissipative.
Yeah, I see. But here, no, I'm not.
Okay.
I'm not going to take S be complex. But yeah, I see what you're.
Question.
So the whole thing is to show. Yeah.
It's just about E. But E was defined for undirected graphs.
Yeah. So right now,
how do you enter directions into E? Because it's symmetric in I and J, right?
So here, I say, when you look at this dynamical, I took the dynamical system and I split it into two. They're kind of semi-conjugate system. This one can be handled using total S energy. But of course, I haven't told you what it is. But this one, I will not use the total S energy. So what I'm going to tell you now does not use the total S energy. So there's no point answering a question because I'm not using it. For the reason that you're saying. So no, okay, let's speed this up.
What should I think of the volume of this red dot?
So the volume of this red dot, the statement that I thought I had a slide for that statement.
Go back. There the dots have different areas.
Yeah. I had a slide that stated the theorem. Where is my statement of the theorem? No. What happened? Yes. This. Generically means the following. This, I could say that with measure 1. With measure 1.
But with respect to what space, so.
Yeah, with measure 1, this thing is periodic, but it's a stronger statement than that. Measure 1 is not good enough for computer scientists. Because, for example, we might only be interested in rational inputs, where rational input has measure 0. And so you could be measure 1, it works for everything except rational inputs. So it's a stronger statement. It's the following statement. You pick your initial condition, okay, and then there exists a tiny ball around it, and basically most of that ball is safe. There's a finite decomposition of that ball, which therefore includes most rational numbers. In other words, you can perturb this if you have to. Most likely you don't have to, but you may perturb it to a rational point if you want, to any point you want. It's not just with a high probability. It's a much stronger statements like that than that. It's the complement that has measure 0. So, but I don't want to get into this. But anyway, that's the ball. Whoever asked me the ball is the perturbation thing, basically. And so the trick is to show that it's not chaotic because, and you might think that because the eigenvalues are never greater than 1, the system cannot possibly be chaotic, but that's wrong. There are systems where all the eigenvalues are close to 0, which are chaotic, okay? And even in 2 dimensions. And in fact, this thing can be locally chaotic. If you remove the generically thing, and you can say, well, is that true without the word generic? And the answer is no. You can actually, I mean, basically you get somebody to hit this thing all the time. And they bifurcate, and each children does the same. And it's very hard to arrange for this to happen, like the worst case scenario. So anyway, at the end of the day, you prove that generically, this business, because it looks like springs, as Jennifer said, there's a bunch of springs, so there's something dissipative about it. And the whole thing has a Hausdorff dimension that's somewhere stuck between the dimension of the space and a little lower. And that's why the whole thing, that's how you avoid chaos. So these were really tools, I guess, from dynamics, but the way they're treated is really, I think, from an algorithmic standpoint. I want to make that clear. So this is the end. I just want to conclude now maybe with, I have an agenda, obviously, and I've just scratched the surface here. I mean, that's why I'm much more interested in the program itself than the specific results and so. You can tell me the results are useless. Probably I will agree with you. So, but what I really want to pay attention to is the following thing, is that, so as I say, we have very powerful tools to deal with this. So why do we need more? Well, first there's the soft answer, which nobody can disagree with, that computer scientists and people doing algorithms for decades now have thought somewhat differently. So they have a different culture. And to merge cultures, not merge, but to bring cultures together, scientific culture, is always a good thing. There's always good things happen when people look at the same elephant from different angles, because they have different tools. One cannot possibly disagree with that. So that's the soft answer. But there's a harder answer, and maybe more controversial. One is the fact that the sheer descriptive complexity of these natural algorithms and their expressive power. By descriptive complexity, I mean the following. If you look at the sciences of the 20th century, where mathematics has been astonishingly powerful. I mean, when you look at physics of the 20th century, it's just breathtaking how much you can write a page or 2 pages of mathematics, and that explains, a lot of what will happen in this room, down to the quantum level. Now, let's make sure we understand what I'm saying. I'm not saying that those things are not complex. They're terribly complicated. I mean, physics is terribly complicated. So, but what I'm saying is that the basic equations fill just 1 or 2 pages, 2 pages if you have a big pen. And then you spend the rest of your life trying to understand the consequences of these equations. But the equations themselves are not that bad. And now, that is fundamentally not true. I mean, nobody thinks that somehow we'll figure out the brain with 5 differential equations, and bingo, we're done with that. Those things are probably inherently, whether it's biology or the web or social networks or, they're probably more like Russian novels where there are lots of different actors and just things are just descriptively, just to describe what it is. This is very complicated, let alone to make statements about it. In that sense, there's a big difference. And there are also some notions which somehow do not really appear in classical mathematics to that extent. One is communication. There are just new things, new patterns that happen when I mean, many of you have studied, networks and engineered networks to provide all these sort of new math that comes out of this, which is really fascinating because communication really adds expressive power. That of agency also, where, I mean, each node has a life of its own, has a way of thinking of its own, and it might be autonomous, might not be autonomous, it's influenced. That sort of agency also is different. I mean, in physics, when you have Newton's equation, it applies to all the particles. I mean, it's not like, oh, not this one or something. And so there's this universality that really is not going to occur so much. And the third is it's very heterogeneous. Now, that's true also in physics. I mean, not everything is the same. But here it's taken to an extreme where you really have different conceptual behavioral entities that compete for resources or something. And they're really fundamentally algorithmically different. Okay, enough of this. Thank you. Sorry, I talked too long. Yeah.
Which is like this terrible function. What happens if you slightly perturb the belts?
Yeah, that's a good. So, yeah, because I was bothered, somebody would ask me this question. I actually worked out that the theorem can handle perturbations. So in other words, there is a noise model that I define very carefully, that you can turn on if you want. I mean, if you don't want noise, there's no noise in the result. But you can turn on that noise, and every step there will be a little bit of noise, and the same result holds.
As a lower bound?
However, yeah, as a lower bound and as an upper bound. However, for the sake of disclosure and honesty, this will only be true if the entropy goes down. So think of a random source that provides noise. And the entropy will have to go down for this result to hold. Let's say you have a constant source of entropy at each step. Then this totally collapses. Totally. It's not like a little bit more work will make it work. I believe this is completely, I think the result is false.
But what does your second result have to say about this flocking result? I mean, you know that there's some S energy function for the blur.
No, so the flocking is much more difficult.
I see, it's not.
It's a linear function field, right?
Oh, but it's not.
No, so flocking is a different order of logic. Maybe I can briefly say why. So think, for example, of opinions. These are agents, these are points in space. And then they move around. But the network is defined entirely by their position in space. Okay, if they see each other, if they are, that's how. Now, in the case of birds, we do this for the velocity. The phase space is really velocity. Now, the averaging is over velocities, because we average velocities. But the network is not defined over velocity, it's defined over positions, which is the integrals, which means it's not Markovian. The network needs to look at all the past in order to know whether there's an edge or not. And this is why it's significantly more difficult.
Good. My question about noise was not that like at each stage you put noise, but rather on the initial state, and then there's no entropy, right? I mean, because you just stop.
Yes, then you're right. Yes.
Then that may be what's happening in nature, right? I mean,
yeah, oh yeah, yes. Yeah, oh no, I mean, I'm not claiming that.
So if you
none of
analysis
this
can maybe show that like in polynomial time they converge to all those.
Yes. I mean, again, when people say, why do people work on worst case analysis? It's because it's simpler. And I believe what you just said, but I don't know how to prove it. I mean, the tools simply are not powerful enough to do that. It's much more difficult. But I believe that's true. No, I believe that's
So
true.
why can't you, if you, instead of having your birds move in space and velocity, what if you make space and velocity, what if you do your movement in phase space? Then you
No, but it can be very different velocities, very far away, but still close in space. and
No,
still
but
not
see,
overstep,
his
so-
graph is a projection or not a projection. I mean, it's some kind of integrals. So he keeps forming his graph in a different space than.
But that would be fine, because you would have a 6-dimensional space and the phi function only depends on 3
Yeah,
coordinates.
but now your phase space would not be independent. I mean, you'd be really navigating in the sub-manifolds, lower dimensional manifolds of these things, because it would always be true that your position is the integral of the velocity
That's
in the
forbidden
past.
by your.
No, that's not. But it means that, say, I mean, this technology. I mean, maybe that's what I'm doing in disguise. I mean, yes, it's maybe yes. Maybe that's just another way of phrasing it. Yes, it's. But it would be more complicated because the phase space simply is going to have more. If you put the velocity and the position in the phase space itself, then the graph will be, determined in funnier ways. When you average, it's not clear what the influence is on the graph in the next step.
Okay, maybe.
Well, yeah, I'm sorry.